So off by a factor of 1,000,
That's a lot, isn't
usually. Yeah, I'm not,
it? Yeah, so I
I
don't
mean, you
know.
obviously typed the other one, you typed this in correctly.
Right.
This is in correctly.
I'm just making sure that to use the E instead of the times. Cause I remember you said before we make that mistake where we do 6.67, put hit the times and then the E.
Yeah,
You
that
can't
will
do that.
mess you up.
Yeah.
My calculator, if you do that, you're bringing an extra factor of 10 in. Some calculators presumably will just go, whoa, no.
That's what mine did.
Okay.
It didn't let me do it.
So in the buttering check thing that you said on homework, it has you put in the equation and then you times it by 6.67 times 10 to the negative 11. I'm assuming it doesn't matter if you do it in the, like, in the problem itself or after, if you get some answer, right?
Yeah, I guess he keeps writing it as big G and then mass 1, mass 2 over R squared. Yeah, it doesn't matter.
Okay, yeah, I just wanted to make sure.
And the reasoning is that I can turn anything into a fraction just by putting it over 1. And when you're multiplying fractions now, you multiply the numerators together, you multiply the denominators together, and you get that.
Cool. Just
So
wanted to make
either
sure.
way, I'm trying to remember in the, yeah, on the top of the first page, I wrote it the way that he does.
Yeah, I just wanted to make sure.
Other questions from 8 or 9?
Can you just do the thinking rank for 45 and 47? I didn't understand this.
45 and 47, planet and the moon attract each other. Rank the force of attraction between each pair. So this is chapter 9, number 45. So we got M and little m, and a distance D between them. That's A. B, double the size of the mass there, and keep the distance the same. And C, we double the size of the smaller mass, and keep the distance the same. And in D, keep the mass the same there, double the little mass, and double the distance. All right, so we're still basically using the exact same formula here. Did something with it, there it is. Now, all we're doing is a comparison, and all we do is multiply or divide. So if I'm looking at G mass 1, mass 2 over R squared, the value of G really doesn't make a difference because they're not asking us to find an exact value here. So I'm just going to let G equal 1. The reason G is the value it is because of the unit system we're using, but we don't have any numbers, so there are no units really. So that's just going to make that equal to 1. So now, what I'm doing is a comparison. The first one just would be big M times little m over D squared. That's A. B, oh, and by the way, making G equal to 1, this is known as naturalized units. This is something that theoretical physicists do because they don't feel like dealing with it. So they also sometimes just let the speed of light equal 1. Figuring that there's a unit system where that's true. B, so it's now 2m times m over D squared. So right off the bat, this is bigger than that by a factor of 2. C, we doubled the smaller one, so that's big M times 2m over D squared. And then for the last one, we doubled the smaller mass, but we also doubled the distance. That's big M times 2m over 2d squared. And don't forget, we're also squaring that 2. That's part of the distance. So that's two big M, little m, over four d squared. Oops, I wrote that wrong. That's better. Over four d squared. Or big M, little m, over two d squared. We actually could simplify it one step further. Because they didn't tell us the masses, why don't we just make them equal to 1 also? If that's the case, then heck, let's just make the distance equal to 1 also. So A is 1. B would be 2. 2 times 1 divided by 1 squared. C is 2 also. 1 times 2 times 1 divided by 1 squared. And D would be 1/2. 1 times 1 divided by 2. Because the ranking does not actually depend upon the mass, as long as big M means the same thing every time, and little m means the same thing every time. So B equals C. So in presenting, B equals C is bigger than A, bigger than B. Or some people will write B equals C, comma A, comma B. Got it?
Yeah, I was just confused on how the B equals to C, but I get it now.
And you said 46?
47.
47. Pretend you're falling into a hole, bored completely through the earth. It would take about 40 minutes to actually go all the way through, by the way. Discounting friction and rotational effects, rank your greatest least positions for those positions, speed and acceleration. And it was, so there's the middle of the earth, that's B, A, assume C is same distance from B as A is, and then B. So if you're in the middle of the earth, what is the gravitational pull on you? Nope.
Would this be 0?
It would be. We talk about the center to the center distance. If I'm standing on the earth here, that I'm being pulled by the earth and the force is downwards. That actually is a resultant. I'm actually being pulled to every single little tiny mass on the earth. So every single bit of earth is pulling on me, and if you add them all up, it adds up to a force acting straight towards the middle. If I'm in the middle of the earth, or whatever's in the middle of the earth, it's still being pulled on by every little mass here, but in this case, all the forces are countering something else on the other side. So the force, the gravitational force on you in the middle of the earth is 0. Remember that F equals ma. And so, I guess part B was ranking accelerations. So the acceleration is directly related to the force, and the acceleration is the greatest when you are closer to the surface. So D is going to have the greatest acceleration, B will have the least. And then A and C, based upon my reading of the picture there, A and C are the same.
Yeah, why is that? Like, why? I can understand like D, but how do, I don't understand the other ones.
Good. Are you good with B being 0?
Yeah.
All right. At A, if you imagine that you're being pulled by every part of the earth while you're at A, there's far more earth below you than above you, so that's why there's still acceleration. The net force is not zero, but you are being pulled up some, because there is part of the earth above you on that side of you. So all of this is trying to pull you up, all of that is trying to pull you down. And so there's a net result downwards at this point. But again, I have more pulling down than pulling up. So that's why it's less there than at the surface. At the surface, it's all pulling you down. At this point, only some of it's pulling you down. In the middle, you're being pulled every way. And C is similar to A in the fact that they're the same distance. The only difference is your acceleration at A is this way, and your acceleration at C is that way. And then in terms of speed, yeah, if I dropped into a hole, I'm gonna get faster the farther down I go. So I'm gonna be fastest the closer I am to the middle. So for speed, so I guess the problem A is speed. Speed, I'm fastest at B, and then A equals C, and then D. And then for acceleration, my acceleration is greatest at D, then C equals A, then D. They are reverses of each other, but there's no reason why I wrote A equals C there and C equals A here for any particular reason. A equals C, C equals A, whichever way. All right, other questions from 8 or 9? Questions from 8, 9, or 10?
27 and 10.
27?
Yes.
You're flying an airplane that flies horizontally. That is convenient, with a speed of 1,280 meters a second. An engine falls off. Assume it takes 30 seconds for the engine to hit the ground. Very similar to the example that we did in class when I shot a ball horizontally and had one fall at the same time. So an object being projected in one direction, if it's shot horizontally, it's going to take the exact same amount of time to hit the ground as one that falls straight down. So in this particular case, this thing is being basically shot at 280 meters a second when it falls off. It's kind of like the airplane sort of slings it. It's shooting along at 280 meters per second, keeping it from falling, but as soon as the engine detaches, then the plane is irrelevant. But before that, the plane is very relevant, 280 meters a second. It tells us 30 seconds to fall. And so the first question is, show how high up the airplane is. So we're using the free fall, an object starting at rest, because there's no vertical velocity to start with. So delta x equals 1/2 gt squared, or d equals 1/2 at squared, or various variations like that. So 1/2 times 9.8 times 30 squared. Or if you use 10 here, it'll come out to 4,500 exactly. Without 10 there, it comes out something close to it.
4,400.
4,400,
10.
10. Units?
Meters per second.
It's a distance,
Meters.
meters. This is meters per second squared, and then this is seconds, which you're squaring. And then they said, Joe, it's 4.5 kilometers, 4.5 kilometers. What if I go from meters to kilometers, I'm moving the decimal 3 spaces. And so that would be 4.4 kilometers or 4.41 kilometers. He said 4.5, I think he's using 10 instead of 9.8. That's the difference.
In there, you wrote, you said y equals 5t to the second. I was trying to figure out how you got 5. I don't know.
The 1/2 10. So I guess he is using 10.
Okay.
Part B, show the horizontal distance that the aircraft engine moves is, during its fall, is 8,400 meters. Well, I know the time, I know how fast it's going horizontally. All the acceleration is downwards because if we look at the force diagram, weight is acting down, it's not affecting any horizontal motion. And of course, we are ignoring air resistance, which I think he actually states. Yep, ignore air resistance. And so that's just a distance equals rate times time, delta x is equal to vt, average velocity times time. Do it that way. Distance equals rate times time, several ways of, you might have seen it in your lifetime. But it's going 280 meters a second for 30 seconds.
Yeah.
Yes.
And then again, meters. And if the airplane somehow continues to fly as if nothing had happened, where is the engine relative to the airplane at the moment the engine hits the ground? Well, where is the airplane? It's traveling 280 meters per second horizontally. After 1 second, how far is the plane gone?
280 meters.
After 1 second, how far is the engine gone? Horizontally.
80 meters.
After another second.
560 meters. No.
And that's the answer to either question I just asked. Because they have the same horizontal velocity, horizontally, they will travel the exact same distance. So as, see, if I check my coordination here. So as this goes, they should be right over top of each other. And so where's the plane when it hits?
Over the,
Somewhere right there. And then if you take air resistance into account, then I guess you have to take into account the shape of the engine. Anyway, any other questions about this? Other questions from 8, 9, or 10?
Yes, I have, actually, it's the next question, question 28. I couldn't figure out how you're supposed to find out how far the bullet drops in this problem.
I didn't think that was in the
It wasn't. Fires his rifle at target 200 meters downrange. Bullet moves horizontally from the rifle. Barrel speed of 400 meters per second. How far does the bullet drop in a straight line? All right, so we have to ignore air resistance. This is sort of a reverse of this problem. and the fact that we now know the horizontal distance, which was 200 meters. Should I get it backwards? Yeah. So it's going 200 meters, with an initial velocity of 400 meters per second, and it's going to fall as it goes. So, using this equation, because horizontally we know that information, this is 200 is equal to 400 times time, so times a half a second. And so now to figure out how far it falls, well, we're using this equation over here to figure out how far does it fall in half a second. So the distance it will fall is 1/2 times 9.8 times 0.5 squared, which is, that's a quarter, about 8, so about 1.25 centimeters. Or, no, that's not right. .25 meters.
122.5.
122.5?
Yes.
You did
Oh,
0.5 squared?
No, I did 5, so.
So it's gonna drop a little over a meter. And to hit a bullseye, why does Bob adjust his gun sight so the barrel positions upward a bit when he aims at the target? Well, because it's gonna fall. There's a classic problem done in a lot of physics classes until, I guess, ultimately, it's a cruel problem. It's called the monkey shoot. That you got a monkey here in a tree. And you aim a gun at it. So that